Proper start.
Sir.
Okay. So today we are starting the last part of the subject of electrolytic systems and control. As the presentation says, we will be discussing about stability and performance analysis of linear systems. The layout of the presentation is we'll start with a simple example that is basically a recapitulation of what we studied in the last part. For a nonlinear system, we split it into two parts, a nonlinear part and a linear part. From the nonlinear part, we construct a feed-forward controller to assess the major amount of voltage excitation or electrical excitation that is needed, and about that nonlinear part, we achieve a small linear part for the containing the error and error-like small terms, and that helps us in assessing the stability. That is the major focus of this part. So that is why we concentrate only on the linear stability theory, because even if the system is nonlinear, we ultimately assess the stability based on the linearized error dynamics. In the example that I will give, the point might be a bit more clear. Then the other parts will be taken care of. I am not just reading it out. As we will proceed, each will come one after another. So here we are considering an example. We have a system whose ordinary differential equation presentation is like this. We can consider R to be the response. It's a second order equation in which this A1, A0, B, these are positive quantities. You can consider this equation very representative of a solenoid activated by current and pulling a magnetic substance separated by a spring close to it. So the initial gap is 0, and with excitation, as the voltage increases, the excitation force increases, and that causes this gap G0 to close. We want a specific type of closure for this gap, where D stands for the demand, and of course the demand could be anything between 0 and G0, because there is a solid length of the spring beyond which the gap can never be closed. So the demand eventually has to be less than the initial gap. In this equation, this delta represents some kind of disturbance, and that may arise from the friction between moving components. If this solenoid is actuating a spool valve, then this delta will contain all the flow force components, and as we know, the flow force we compute in terms of some Launch analysis. Launch analysis means we consider a particular velocity of the cylinder piston, and based on the motion of the cylinder piston, we assume a constant discharge, and the discharge divided by the opening of the meter port gives the constant flow velocity with which, in the form of a jet, the flow enters through the metering ports. But just as we are considering a single representative velocity, that's why we call it a lump analysis. But as you have studied fluid mechanics, you will be knowing that at all the points the velocity will not be constant, especially at the edges where we have the spool land and the slip land. There, due to the no slip condition, the velocity will be zero, and in the intermediate region there will be a variation. So that is the actual variation. Instead of the actual variation, we are considering an average form of the velocity in order to compute the flow force. So that flow force estimation might be reasonable, but there are approximations in it. So that's why we're telling delta is known and major part of an uncertain disturbance, but there will be an unknown part as well. So because of that, uh, just 2 minutes, I'm coming. So sorry for the interruption. So we were talking about this equation where the disturbance part I was explaining. Now, in order to, of course, because of this term, we clearly see it's a nonlinear equation, and when we have this kind of nonlinear form, what we do, we pretend that this voltage, it is composed of two parts. One is the feed-forward part, which dominates over this feedback part. And a PID feedback controller is formulated in this form, where this feedback voltage, a part of it is proportional to the error. Error is the gap between the demand and the response. So the other part of the feedback control is proportional to an integral term of error, and the third part is proportional to a derivative term of the error. Why we use this kind of form, that also we'll try to explain. So, but first, the splitting. So, starting from this nonlinear equation, and this equation we restructure as this, and with these assumptions, the first part we can straight away say, just if we substitute R by D and V by Vf, this equation will be reproduced corresponding to demand and the feedback voltage. Because, I mean, the difference between D and R is not high, and the difference between Vf and V is not that high. So, this gives us the feed-forward composition part. And just because the demand is a known form of, say, if we want a sinusoidal motion within the gap, then D will be a sine function or cos function, and depending on the given function, we can take their derivatives, and this d double dot, d dot, d, etc. becomes known function of time. And in this equation, we can clearly see that the only unknown is this voltage. So this equation we can exploit to obtain the feed-forward voltage part. And now if this in this equation, instead of just replacing d r by d, we replace r as d minus e, and instead of replacing v by vf, we replace v as vf plus vb. So in that case, this equation will have both the derivatives of d dot, d double dot, e double dot, etc. And that if from that composite equation, if we subtract this equation, we obtain the linearized part of the error dynamic equation. So simply you can see d double dot minus e double dot is this r double dot term, d dot minus e dot is this r dot term, d minus e is this r term. Now instead of v, we have vf plus vb whole squared. So from that, vf squared term has been taken out, and with vf squared we will be having 2 vf into vf. So this is the other term that is emerging, and since vb we are considering is small, the vb squared term will be thrown off, and in the denominator we will be using, instead of d, r minus e. Sorry, instead of d, r minus e, yes. No, r plus e, right? It will be r plus e, and if we substitute that and again throw away the e square part, then the resultant equation will be of this form, and the other, as a result of these various approximations, will have a small delta term arising that we just place it here, but we do not know, we only know it is small. And if you look at this equation, though this vf square, d square, these are present, but vf square is known here. In this equation, the unknown part is vb, and we do not have any, as vb is small, and we have neglected the vb square term, so we don't have any square of voltage term and square of E term, because E is also small, so E square is also small. So in this way, this error dynamics evolves as a linearized error dynamic equation. Crisply, we write it in this form. So now from this equation, we obtain the equation for the feed-forward voltage. As I was telling, it emerges as a function of time, because d dot, d double dot, all are known functions of time, and in this equation gives us an assessment of the feed-forward voltage, and this equation we recast by putting for VB this particular term. So in this equation, we can, from this equation, we can see, suppose we do not have any this integral term, then at the end of the transient process, what will happen? This term will remain A0 into E. This term will remain, and because of this delta, there will be a small offset with respect to the given demand, because of the presence of A0E plus some P term here equal to delta. So delta divided by all the coefficients of E is the steady error that will arise when all the transient phase will get over. So because of that, we need to add the integral term also, and Also, we know that in order to for the stability of this equation, all these coefficients should emerge as positive. Even if we do not remember in the course of this class, we'll be knowing it, rather we'll be recapitulating it, that in order to have a stable solution, all the coefficients of this differential equation should be positive. So, and this A1, it emerges as negative because of the inherent nature of the plant, where we do not have any control, but we have some control imposed through this feedback, and in this feedback, the derivative term should be such that that should take care of this negative part, so that if we have this term satisfied, then the coefficient of E dot will emerge as positive. So one part of the coefficient is minus A1 and another part of E dot is arising from this KD into this external term. This external term. So in order to, for the positivity of the coefficient, we should have a derivative feedback, so that it would nullify the effect of this, it could nullify the effect of this negative component. Luckily in this system, we have a positive component available. Had this been negative, this, I mean, the role of the proportional controller should have been to make this positive as well. Okay, so in this way, we see that in order to make all the coefficients positive, that gives us the reasonable bound for these gain values that we should adopt in a particular case. And as I was telling about the eigen, so when all the transient part is over, then this integral e down edt may not be zero. It depends on how the variation goes. So when all the transient phase is over, at beyond that time, if we have a constant value of this integral, and if that constant value multiplied by this exactly offsets this delta, then of course we can clearly say that the steady error will be zero. Okay, so and beyond that time, we call that to be the settling time. That is, uh, I mean, we use as TS in this bound. So that gives us the reasonable estimate for this eigen. Though I am telling it a reasonable estimate, but this delta is not well known to us. If we keep on, if we keep the square terms live, and those square terms will give us an assessment of this delta, and those assessment we can use to find the some reasonable value of ki. I am calling it reasonable because again that is the product of an approximate long formulation for the flow forces, etc., etc. So in actual case, the things could be a bit different. So in real life, we may need to resort to slightly deviated value of the gain values than what we approximate from these equations. Is it clear up to this part? Am I audible?
Yes, sir.
Okay. Now we are considering that we have some error as input to the plant, and we have the response as the output. And this input to output is related by some differential equation in the linear form given like this. After taking Laplace transform in this form, this gets transformed to this form. Laplace transformation is a method that transforms a differential equation to an algebraic equation. It is basically very similar to what we do in our elementary classes, where we take the form of this response to be like this, and if we substitute for this, then this equation becomes like this, corresponding to the homogeneous part, and a transient and another integral factor will arise because of this non-zero input. But that non-zero input will have a transient effect, and after the subsidence of the transient term, the entire process will be dictated by the homogeneous part. So we focus on only the homogeneous part, and then what we do, this function we split in terms of a set of first order terms, and depending on the situation, all these z could be real, or maybe some z would be real, and there will be a number of complex conjugate pair in this form. The real z we are considering in this form, and the complex conjugate we are considering in this form, where j stands for √(-1). So if z has a negative real part, then the corresponding solution will be of this form, and because of this negative sigma, we can clearly see that the response R will keep on decaying with time. Higher the value of zeta y, the absolute value, of course it has to be, it must remain negative, the faster will be decay. And when we have a pair of complex conjugate, then the corresponding to these two roots, the response should be of this form. Again, for the time being, you just accept this to be the form. In a later example, I will try to show really that when we have a situation like this, we really obtain the solution where the decaying exponential part is related to this negative real component of the root, and the complex part forms, say, sinusoidal part in combination of sine and cos. Whether both will exist or not, it depends on the initial state of the system. And here also, as this sigma value increases, the decay of the response becomes faster. So depending, if it is a pure first order, then we will be having only one pole. If it is a purely second order, then we could have two real poles or a complex conjugate pair. If it is third order equation, then three real poles or one real pole and a combination of one complex conjugate pair. So in this way, whatever be the order of this equation, basically we can consider it to be composed by a number of first order parts and a number of second order parts. So that's why the first order equation and second order equation, these are fundamental in nature in order to appreciate the controller performance. Now, as I was telling about Laplace transform, the same thing we, for this block will lead us to this same equation that we obtained here, but instead of this exponential RST, it will give rise to this RS. Okay, so and with all the initial conditions set to 0, the transfer function is defined as the ratio of output to input, and this results in this kind of algebraic equation for S. This denominator function is called the characteristic function, and this equated to 0, we call it a characteristic equation. And as we have already seen here, the roots of the characteristic equation, these are of fundamental importance. If all the real parts are negative, then it gives rise to a stable system. And before moving further, we just consider that we have this response function in the form of this denominator and along with one numerator. Okay, so if we split, we can split this as this S plus P1 and S plus P2. Since we call the denominator function as the poles, we have written this as P1 and P2. So basically, this we split in this form, and their combined form becomes like this. And then if we compare this part and this part, clearly you can see P1 plus P2 is equal to 1, and P1 into P2 is again equal to 1. So if I square it, and then from that, I think we have again so P1 plus P2 whole square minus 4 P1 P2 is P1 minus P2 whole square. So P1 minus P2 will be 1 square minus 4 whole it under root. So P1 minus P2 will be plus minus j root 3, and that will give us P1 and P2 as 1 plus minus j root 3 by 2. That is what I was telling. For a pure second order system, we will be having a pair of complex conjugate root. Then if we go to this equation, this S is equal to this, and in this equation, if we put S equal to negative of this, then we will get one equation to evaluate C1, and if we put S is equal to negative of this, then we obtain an equation to evaluate C2. In this way, we evaluate C1 and C2. Are you able to follow, or should I give some time for you to follow how we have obtained? What I am trying to say, in this equation, if we put S is equal to negative of this, then the coefficient of C2 will become 0, and the coefficient of C1 will be some value, and that we assign corresponding to S, and that will lead us to an equation to obtain C1. By processing that, we obtain C1, and similarly, by making this coefficient equal to 0, we obtain a value of S, and we substitute that value of S here and here to obtain the value of C2 that emerges as this. And once we obtain both C1 and C2, then this response will be simply, for this we'll be having exponential to the power of minus P1 t, and here we'll be having exponential of minus P2t. And if we look that the real part of both P1 and P2 are the same, so because of that, for corresponding to that real part, we'll be having exponential minus t by 2 pulled out, and corresponding to the complex conjugate, we'll be having another. These are the complex conjugate part. One part is minus and the other part is plus. And for the minus part, we have this. For the minus part, we have the coefficient C2, and for the plus part, we'll be having the coefficient C1. When it is plus, we did the exponential, it will be negative, and when the pole is when P2 is here, it will be negative, positive. So in this way, we expand the equation, and if we follow the algebra minutely, we'll finally find that the complex part will get cancelled with one another, and we'll be having a simple equation for the response in the form of an exponential function and a combination of cosine and sine function. And clearly, if this is negative, it indicates that response will decay to 0 as time moves on. Whatever, because of the bounded nature of these periodic functions, the maximum value of the periodic function could never surpass their amplitude. And so whatever be a finite amplitude, if it gets multiplied by a number that becomes smaller and smaller, the product will become smaller. So that indicates an asymptotic decay to 0 with time. So that's why all the time we say, if we have these poles to be composed of negative real part, we have a decaying solution. And in order to have this positive, what is the genesis of this? We split this equation in this form. So all these will emerge positive only when all these coefficients are positive. Otherwise, it is never possible. So one fundamental requirement for stability is that all the coefficients of the characteristic equation must be positive. Is it clear? Okay. So with that understanding, now we just consider a simple first order characteristic function. If the solution is, s plus sigma 1 is equal to 0, and if that is the situation, then if some initial disturbance generates some error, then because of the decaying nature of this sigma term, the error will eventually proceed asymptotically to 0, in this form, higher the value of sigma, faster is the decay. That is indicated in this form. And if we make a plot of this sigma in this kind of plane where sigma is the real axis and omega is the imaginary axis indicated by this j, for the first order equation we will be having only one root like this sigma 1. If it is second order equation, then that second order equation could be split in this form so that we could have a pair of complex conjugate given by this sigma 2 omega 2 and sigma 2 minus omega 2. And again, if the initial disturbance makes the error shoot up to a high value, then because of this negative real part sigma 2 2, we will have some kind of decay. If this sigma is small, then this decay will be fairly slow and it will eventually become zero beyond a particular time. But if we keep on increasing the sigma value, we may see some periodic oscillation prior to settlement to the zero. When we have this kind of periodic oscillation, though the amplitude of error becomes higher, the settlement to zero occurs at a faster rate. So these are simple characteristics of the second order equation. Now, as already I have mentioned, for any order n, we can have a combination of pure Z or complex conjugate Z. But for the stability, all the sorry, all the Z values must be negative. Now, here we have given some examples just to emphasize the requirement of the positivity of the coefficient. If a third order characteristic equation emerges in this form, then we can factorize by our known method where we group s square plus s in one part and s cube plus 1 in another part. This s square plus s is s into s plus 1, and this s cube plus 1 is s plus 1 into s square plus s plus 1. So eventually this is the s cube plus 1 term and this is s square plus 1 term. So if we take this s plus 1 factor common from both the case, this s square minus s plus 1 plus s gives us s square plus 1, and that s square plus 1 is nothing but s plus j into s minus j. So as I was telling, there is a scope for a third order equation to get split into one real pole and a pair of complex conjugate pole. So if that is the situation, this is the say -1 location shown here, and corresponding to plus j minus j, we'll be having a pair of roots like this. So corresponding to this characteristic equation, we have shown the pole like this. Corresponding to this characteristic equation, we have shown the pair of poles like this, and corresponding to this characteristic equation, we have shown the poles like this and these two. And we know when we have this form, it is a purely sinusoidal nature without any exponential I mean, a complex for this complex conjugate will be having cosine and sine function as in the previous formulation we have shown. Now, another equation we are considering where all the coefficients are positive. And in the same manner, we group s cube plus 8 and s squared plus 2s to arrive at this form. Here, minus s and plus s was getting cancelled out. But in this case, what will happen? Will eventually will be having one minus s. I mean, from here we'll be having s into s plus 2, and from here we'll be having s plus 2 into s square minus 4s plus 4. I think if that is the case, it should be I don't. Is into s plus 2. Okay. So, yeah. From s cube plus 8, we will be having s plus 2, that is taken common, and s cube minus 2s plus 4. So that minus 2s and plus s will give us to minus s. But I think instead of this 1, we might be having plus 4. I mean, you please check it whether it will be plus 4 or plus 1. I am not making any correction at this stage. Maybe when I will load the PowerPoint back to you, I will make the necessary correction and upload it. Okay. So, but what I am trying to show here that just positive values are not good enough if the equation is of higher than second order, because even for all positive coefficients in the split form we are finding one real positive root, but here we are finding a case where the real part is not negative but the real part will appear as positive, that is given by this minus half, and the imaginary part is root 3 by 4, and whether it will be root 3 by 4 or not, it will depend on how this correction to this one evolves. Anyway, whatever be the correction, it will remain a complex conjugate pair. So if the equation is of this nature, then we have a root here corresponding to this plus 2, and corresponding to this we have two roots in the positive side of the real axis. When we have roots of this form, clearly because of this positive nature of this real part, the error will keep on increasing with time and it will indicate an unstable situation. So in this plane, if the roots are on the negative half, including the axis, we can conclude the system to be stable. But if any root forms in the positive half plane not containing the imaginary axis, then it will imply an unstable system. So that is the whole interpretation of the plotting of the poles here as shown. And so Here also we arrive at a situation that shows that apart from positivity, we require some additional constraints to be
আমাদের আমাদের এটা
satisfied
আগে চেঞ্জ কর,
for
এটা যদি চেঞ্জ হয়ে
any
যায় তো ভালো,
system
ওইগুলো চেঞ্জ করে না।
beyond third
এগুলো
order
চেঞ্জ না
to
হয়
be
আমি
stable.
এগিয়ে যাচ্ছি না, তুমি ইচ্ছা
So
করে করো আমার।
for that stability assessment, we formulate what we call a Routh array or Routh-Ruiz array, and the array formation etc. is shown here that I am going to explain. So where we start with the
সকাল মানে সন্ধ্যা সকাল বেরিয়ে কালকে আমার রাত্রে ঘুম হয় না, 5টার সময় শুতে গেছিলাম, 5:30 6টার সময়
পড়াশোনা করে
characteristic equation, and we form arrays like this. The first two lines are comprised of the coefficient of the characteristic equation. The first line has starts from here. This coefficient 1 is written here, then one term is omitted, this term goes here, then the third coefficient comes here, fourth coefficient goes in the next line. In this way, starting from the first term, every alternate term is picked for the first row, and starting from the second coefficient, every alternative coefficients are picked for the second row. So if this n is even, say if it is 8, then s coefficient of s to the power of 8, coefficient of s to the power of 6, coefficient of s to the power of 4, coefficient of s square, and then coefficient of the constant term. But if it is say of the order 7, then it is coefficient of s to the power of 7, it is coefficient of s to the power of 5, it is coefficient of s cube, it is coefficient of s, and after that we won't be having any. So whether we'll stop at a1 or a0, it depends on whether n is odd or even. So that is what has been written here. When we stop in the first line at a1, then in the second line we won't be having So if the coefficient of the first line stops at a0, then the coefficient of the second line stops at 0. But if the coefficient of the first line stops at a1, then the coefficient of the second line stops at a0. Okay, so these two happens only if when we have n is odd or even respectively.
আচ্ছা তোর কি সাইন করিয়েছে? হ্যাঁ, তাহলে পিপিটি ঠিক করতে করতে অবস্থা খারাপ হয়ে যাবে। সাইন করেছে এগুলো? সে বলছিল নাকি সাইন করেনি এই তিনটে 33045টা।
Now, after these two lines are formed, then the later array goes like this. The formation of d n minus 2 is this multiplied by this minus this multiplied by this divided by this. Formation of this is this multiplied by this minus this multiplied by this divided by this. So when we go for the next term, this multiplied by this multiplied by this divided by this. In this way, this series will be formed.
আমি তো সিনেমা
And
দেখছিলাম
once we complete this row, then for the subsequent row, similar exercise will be repeated. So if we clearly see, this coefficient is this into this minus this into this divided by this, and this coefficient is this into this minus this into this divided by this term. So this way we keep on forming the array, and we realize this zero will move slowly towards this side, and at the final level we'll be having only one
এগুলো তো সিভিল ওয়ার চলছে তার জন্য
non-zero term here. This has been explained in terms of the equation that we were discussing last, that gave rise to one positive
না 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 চীনে
real
পরিবর্তন নেই
pole
বাবা
indicating
চীনে পরিবর্তন তো
instability.
কি বলছিস
Now, instead of A1, A2, etc., here
না
we,
চীনে চীনে
of,
হচ্ছে
for this
vote হয়।
equation
ওই
we,
আমাদের পলিট ব্যুরো
in the first time we put the coefficient 1 for corresponding to this, then we omit this, and this
হ্যাঁ
coefficient
ওদের ভোট
becomes
হয়
the
মানে
second
ওদের
part,
ব্যুরোর প্রচুর
and
পাওয়ার
the second time we form starting from the second coefficient and then the fourth coefficient. Once we form the first two lines, then
প্রতিবারই হয়
this
ভোট
coefficient
কেন হবে
is
না? তুই দেখ
1 into 2 minus 1 into 8, that is minus 6 divided by 1. So it becomes minus 6. And
না গণতান্ত্রিক অধিকার হিসেবে
corresponding
ভোট
to
হয়
this
কিন্তু
equation,
যেমন
1
আমাদের
into
এখানে
0
হয়
minus 1 into 0 divided by 1, that gives us a 0. That is what I was trying to say. We clearly see an inward movement of the zeros.
কোথায়
Here,
না
had we interested, we could have put 0 here, but in this line, 0 has moved forward by one column. Now, in the next line, we have minus 6 into 8, that is minus 48, minus 48, minus 1
চীন তো
is
কমে চীন তো কমে
minus 49, minus 49 by 6 is
কেউ ছিল
plus 49.
ওটা 11তম ওটা লেখাই আছে পাশে 11 জি কেমন করে চলে হালকা একটু হাসি মুখে মুটকি হাসি
মুচকি হাসিটাই হচ্ছে ডেঞ্জার
হ্যাঁ মুচকি হাসি হালকা আর এরকম করে চলছে
কি আর একটা পেজ বাকি আছে
Now, that is the relationship between this generalized array formation and a particular array formation. Next, what we do with this array? Without proof, the statement goes like this: if all the coefficients in this first column are positive, then all the roots lie on the negative part of the real plane, so the system becomes stable. But if there are sign changes in the first column, then number of unstable poles are equal to number of sign changes. So if we look at this formation, we have one sign change, positive to negative here, and then negative to positive here. So we have two sign changes. So we'll be having two unstable poles. That is what we infer from the route array. And if we go back to our factorization exercise for the same characteristic equation, we see really there are two unstable poles. Okay, so that is in a way gives us some satisfaction that what we saw by proof factorization, that is getting matched by the hypothesis provided by Raut. একটু পরে কথা বলছি, হ্যাঁ, ঘন্টাখানেক বাদে। Okay, so now another situation may come that this kind of processing leaves us, provides a zero here. Then this zero should be considered as a small epsilon, where this kind of zero will appear. Suppose instead of 8, we have 2 here. Then instead of this 6, we'll be having a 0 here. So when both the lines are 1 and 2, of course, instead of this -6, we'll be having a 0 here, and this 0 will be treated as epsilon. Then this term will be 8 epsilon divided by 8, right? Sorry, 8 into epsilon minus 0 divided by epsilon. So here this 49/6 by, instead of this 49/6, we'll be having okay. So here we see in the first column, when the equation is s cube plus s square plus 2s plus 2, it goes like 1, 1, epsilon, and then 8. So there is no change of sign in the first column. If that is the situation, then we conclude that this is a stable system, since there is no change of sign in the first column. How Raut array is used for the assessment of the stability, I believe it is clear at this stage. In the PDF portion that we will give, in that a few more examples will be given, but I believe this particular example that I have discussed here is good enough to establish how these rules are used for the assessment of the stability. Now, before ending the lecture today, uh, after this, I mean, corresponding to this example, we are just showing a generalization that if we have a nonlinear system, then the demand is put into a feed-forward controller that gives us the estimate of the feed-forward voltage, and that same demand is transferred into another controller block corresponding to the feedback controller, where the response is also fed back by a sensor, and their difference constructs the error, and that error is processed in a feedback controller like PID controller that will give us an estimate of the feedback voltage, and by adding these two we'll be getting the total voltage, and the total voltage will drive the nonlinear system to generate a response. The nonlinear system could be open to outside disturbance as well, and that will influence the response. The objective is to obtain this obtain response that is close to this demand, and what is being achieved, that is measured by the sensor to the feedback controller. So corresponding to this, we have this diagrammatic form. We have a nonlinear differential equation in terms of the response and the excitation voltage, and this response has one demand part and one error part. This total voltage has one feed-forward part and the feedback part, along with these assumptions. And this assumption, as the result of this assumption, is one algebraic equation for VF in terms of the demands and their higher derivatives. And from that voltage equation, along with that voltage equation, we also obtain one equation for the error dynamics, where we have the feedback voltage that we manipulate so as to ensure that error proceeds to zero in either asymptotically or over some finite time. So, I mean, the generalized representation of this example problem has been shown here in a cryptic form, and out of this lower block basically forms as is essential for the assessment of the stability, where we have the demand and response feedback comprising the error that is processed by a feedback controller, and that drives a linear dynamic system corresponding to the linearist part of the system to generate the response. After Laplace transform, this dt gets to this ds, this et goes to es, this vt goes to vs, etc., etc. So instead of t, because of this transformation, all t functions becomes s functions. So that is the result of the Laplace transformation. So now, if we process this block diagram, then this Rs is this input into this, that is we write as Gs into Vs. Now this Vs is nothing but Cs into Es. So that is what we write here. Now this Es is nothing but Ds minus this one. This one is equal to Rs into Ss. So ES is equal to DS minus RS into SS. So that is the equation we obtain by using these blocks, and then if we just pull this RS term and group it with it, then the coefficient of RS becomes 1 plus this GS CS into SS, and in the other side we have this term left out. So as I have told, the transfer function is the ratio of output by this input. So RS by DS becomes this particular form, and in this form, if we have this kind of situation that this GS, CS, SS is their amplitude is well beyond 1, then we can drop this 1 in relation to this. Maybe it appears to be a bit difficult at this stage. How to now say in this SS block we have a term like S into 5, and the GS has the lowest order term 1, CS has the lowest order term 1. So 1 into 5 will be the constant term that will emerge from this block, and of course that 5 is much greater than 1. So if that is the situation, then we can neglect that 1 with respect to that 5 that arises from the product of GS, CS and SS. So, and if we do that, then the response becomes simply 1 by transfer function of S. So by suitable choice of the constant in the CS block, we can really make it like this. And the advantage of this is that if we use a precise sensor whose transfer function is known, then the response does not depend on the uncertainties in GS. GS is the plant transfer function, and the plant transfer function is basically arises from this initial governing equation, and this initial governing equation is dictated by the physics where we do not have any control. Okay, so and where we do not know everything in the minute in its greatest details regarding the flow force. Already I have told we use a model, but that is a model. It must be having some kind of uncertainties involved in it. So because of those, this block GS will have some kind of uncertainties arising from the system itself. But if we choose the controller in a form that allows us to put this simplification, then under that simplification, the role of the uncertainties gets completely filtered off by the sensor accuracy. The sensor accuracy provides the good matching between the demand and the response, because we do not have any influence of this GS here. And for the time being, we just conclude that the response and demand, their correlation is given by the sensor accuracy itself, and whether that will make RS equal to DS or there will be a gap between RS and DS, that we will study in a later class, not today. Today we will end soon with this particular slide itself. The other conclusion of this slide is this: because of this kind of operation, the closed loop function, we have some numerator and some denominator. And we see in the denominator, we have one block extra in comparison to the numerator block. So this helps us to conclude that the polynomial of the numerator polynomial is of lower order compared to the polynomial of the denominator term. So because of that, normally we end up, not normally, always we end up in form like this, where the denominator polynomial is of higher order than the numerator polynomial. Instead of s, it could have been just one alone. Okay, so that is another part that I wanted to emphasize, and that note that what I have told, the denominator is higher order than the numerator, that note has been left here. So with this, I conclude this part, because the time that I had up till now, I could not prepare the transparencies for the remaining part. The remaining part I will discuss in the coming Wednesday class, and if you require, maybe one more online lecture I will give, so that you can have the material delivered in the online mode as well. So with this, today I want to conclude. Unless and until if you have any question. Any question? Any question?
No,
Hello?
sir.
In that case, should we stop today?
Okay, sir.
Thank you.
স্যার
বলো।
বলছি স্যার এই ওয়েডনেসডে তাহলে অফলাইন ক্লাসটা আপনি নেবেন?
ওয়েডনেসডে তুমি কি তুমি যদি চাও যে ওয়েডনেস ক্লাসটা দরকার নেই, পুরোটাই অনলাইনে দিয়ে দেবো, আমি অনলাইনে তাহলে তৈরি করে রাখবো।
স্যার আপনাকে জিজ্ঞেস করছি, আমি তাহলে সমস্যার একটা এক্সট্রা ক্লাসের জন্য বলছিলেন, তাই আর কি।
ঠিক আছে, তাহলে সঞ্জীব নিয়ে নিক। আমি তাহলে তাহলে নেক্সট উইক রবিবারেই আবার, তাই তো?
হ্যাঁ
এই
স্যার, আপনি
টাইমে?
যা বলবেন।
হ্যাঁ
স্যার আপনি যা বলবেন।
হ্যাঁ, তাহলে আমি কি বলবো, আমাকে একটু টাইমটা লাগবে। আমার পাওয়ার পয়েন্ট তো আজকে আমার এখানেই খতম হয়ে গেল, এবং তাও তো দেখছিলে আমি লোকালি কারেক্ট করতে করতে যাচ্ছি, আমি কারেক্ট করার টাইমও পাইনি। ওকে,
আচ্ছা স্যার।
সেক্ষেত্রে আমি 10:30 আমি নেক্সট অনলাইন ক্লাসটা নেব।
হ্যাঁ স্যার, ওইটা খুব সুবিধা হবে স্যার। নেক্সট সানডে স্যার, সানডেই নিন তাহলে, প্রবলেম কিছু নাই স্যার।
ঠিক আছে, ওকে।
ওকে
কারণ আমার স্যাটারডেতে আমার পিজির একটা অনলাইন ক্লাস নিতে হয়, আমি সেই কারণে স্যাটারডে পারবো না, সানডেতেই নিতে হবে।
স্যার আরেকটা কথা ছিল স্যার, বলছি আপনি স্যার এই ইয়ের পিডিএফটা স্যার কি পাঠিয়ে দেবেন?
না, আমি পিডিএফটা আমি ঠিক আছে, আমি আমার কাছে যেটা আছে তুলে দেবো, বা রানাকে বলছি, রানার কাছে যদি কিছু আপডেটেড থাকে সেটাকে আমি তুলে দিতে। আর আমি যে পাওয়ার পয়েন্টটা থেকে আজকে ক্লাস নিলাম, এই পাওয়ার পয়েন্টটা আমি ফিনিশ করার পরে তুলবো, না এখনই তুলে দেবো?
না স্যার, ফিনিশ করার পরেই ওইটা আপনি স্যার দিয়ে দেবেন।
ঠিক আছে, আমি ফিনিশ করার পরেই তাহলে ওটা তুলে দেবো। আর আমি আজকে রানাকে বলছি, হয় রানা তুলে দেবো বা আমি তুলে দিচ্ছি। ওকে
ওকে স্যার, স্যার তাহলে পিডিএফটা দিয়ে দিলে স্যার সুবিধা হয়ে যায় স্যার।
ঠিক আছে, ঠিক আছে, ওকে ওকে,
ঠিক আছে।
ওকে স্যার, থ্যাংক ইউ স্যার।
Welcome.
Thank you, sir.